My name is Pan. Thanks for coming to my talk. Today I'm going to introduce the Dejavu, a system that is able to leverage prior knowledge to enhance video conferencing quality. So if you ever feel frustrated with video conferencing, with Skype or Hangout or FaceTime, you may agree with me that video conferencing, especially over wireless link, can have very poor video quality. Here are several reasons. The first reason would be that the uploading bandwidth of wireless links, like LTE or Wi-Fi, tend to be much lower than the download link bandwidth. Here, the speed test result I obtained in Palo Alto, I get a pretty good single coverage, so I can get a download speed for more than 30 megabits per second, which is twice as the US national. Loading bandwidth I can get at the same location is only 2 megabits per second. Video conferencing applications has a strict requirement for interactivity, which means that the end-to-end delay has to be small enough to not hurt the user experience. For example, the delay has to be lower than 200 or 300 milliseconds. As a result, video conferencing applications tend to send at a very conservative bandwidth, saying that here I'm showing a plot that the available bandwidth is something around 1 megabits per second to 1.5. Well, at the same time, the video conferencing applications is only using less than 300 kilobits per second. As a result, this is what you are going to see during the video conferencing. So here is a video clip for the video conferencing. You can find that the writings on the whiteboard tends to be washed out, and the edges of the human bodies are pixelated, and there's a lot of compression artifacts along the moving objects. There are a number of solutions for better video conferencing at different layers. So starting from the physical layer, so there are works on the millimeter wave or using MIMO technology for higher link bandwidth. Also, there's a lot of work on the transportation layer by building a better congestion control protocol for video conferencing. Well, at the same time, there's a lot of person working on the video codec side. They're trying to develop a more efficient video codecs for the video conferencing and the general video applications. Today, what I'm going to introduce is Dejavu, system that is working on the application layer for better video conferencing solutions at the other end of the spectrum. Before introducing how Dejavu works, let's first take a look at the key insight that Dejavu leverages in designing the system. On the left-hand side, I'm showing several videos from YouTube. So these are top-ranked videos that is picked from a certain day, and each row represents several frames from a single video. And you can find that there are very few visual similarities from these arbitrary videos. Then, let's take a look at the videos on the right-hand side. So here, there are 4 video conferencing sessions. So each row are still one of the video. You can find that video conferencing sessions has a lot of visual similarities between them. So that is the key side we are using to leverage the visual similarities. To recap the name of Dejavu, it is originally a term to describe the feeling that one has lived through the present situation before. But today, what I'm going to do is to redefine it as a system that optimizes the video conferencing performance by leveraging the similarities between historical and current sessions. So a natural question would be that, how do we leverage the similarities? Our solution is that we net the neural network to learn the similarities. In the training stage, the neural network has both access to the low-quality training input and high-quality training output. The neural network can learn a function between the low-quality training input and high-quality training output. The function, the relationship it has learned will be stored as a prior knowledge into the neural network. In the test phase, the neural network could use a low-quality test input to generate a high quality output by using its prior knowledge to remove the compression artifacts along the human face. It could use prior knowledge to sharpen these edges and make the picture looks better. So let me give you a high-level system, a system-level view about how current system and the Dejavu system looks like. So here, what I'm showing is a traditional video conferencing system. It includes a sender and a receiver. If it's a two-way video, then it just add another path in the reverse direction. And it's, as we have discussed before, it tends to send a low-quality video over the network. The Dejavu system works in two stages. Firstly, in the offline stage, the sender uploads historical sessions of the same scenario and feed it into the server. The server will generate a training data path in the format of low quality and high quality paths and share it with the Dejavu learning engine. The Dejavu learning engine will train a neural network model and share the learned weights with the receiver. Then we come to the second stage of Dejavu, the online stage. In the online stage, the Dejavu quality enhancing neural network could use the weights that is shared by the server and improve the video qualities of the from the sender side. At the heart of the design, the Dejavu learning engine. The Dejavu learning engine is built around a neural network. So this is the neural network we are using. It includes convolution layers as the input and output, as well as a number of residue blocks built in between. Each residue block actually consists of several layers of convolution, random multiply, as well as, most importantly, a direct link from the input to the output. We also did a number of pre-processings to make the network learning more efficiently. We compressed the video into different quality levels to simulate the video that is going to be sent over the network. We also train and shuffle small patches rather than the entire frame, so the neural network can experience larger variation to make it learning more efficiently. Thirdly, we also convert the color image into from red, green, blue into YUV format, where Y stands for luminous, while U and V are two chrominous channels. We then process on the Y channel only because there's a lot of work showing that human eyes are not as sensitive as to the color channels than the luminous channel. By doing this, we can speed up the network inference by up to 2 times. You may wonder what's the performance gain we can get with the Dejavu system. So here we are showing some initial benchmark result on our data set. So we are training on the first 4 videos and test on the last one. So the video we encoded the video at 2 different resolutions from 270p to 540p, as well as 7 different bit rates to simulate the data that is going to be sent over network. We use PSNR, which stands for peak singular to noise ratio, which is essentially a log scale of the mean square error between the target image and the baseline image. So on the right-hand side, I'm showing the result of the PSNR gain we can get. So on the x-axis, what we are showing is the file size. So each point here represents 1 bit rate, so starting from 100 all the way to 2000 kilobits per second. And on the y-axis, I'm showing the PSNR. So the dashed line is the input, and the solid line is the output of the Dejavu learning neural network. We can, from the 540p block, we can find that it is possible to achieve up to 1.3 dB PSNR gain at this resolution, and also we can achieve 1.1 dB PSNR gain at a lower resolution. You may also notice that the PSNR gain we can get decreases as the file size increases. It is because that as the file size increases, the video already looks very crisp, leaving very few room for improvement. Here, I also provide an alternative understanding about the performance number we can get. So here I'm doing some showing some calculation result, saying that what's the bandwidth saving we can get by further compress the video, but use the Dejavu neural network to recover the quality. So the target. So in the end, we'll get the same PSNR with and without Dejavu neural network. So you can find that here we can achieve up to 30% PSNR gain for some of the encoding bit rates. You may wonder that 30% may not sound like a huge number, but I want to emphasize that such a number is comparable as developing a new generation of video codec, which takes several years by a large group of people to complete. Here I'm showing some visual results between the input and output and the reference frame. So let me zoom in into the two of the blue and the purple boxes. So the first is showing the input, and the second is output, and the last is reference. And by looking carefully, you can find that Dejavu neural network is able to remove a lot of artifacts along the face. It is also able to sharpen the edges around the shirt. And on the bottom, we can find that if, for example, here should have an arrow, but the input is totally blurry. But the Dejavu neural network could use its prior knowledge to make it looks much sharper. However, we want to mention that there are still two pieces of future work we need to do before making Dejavu a real working system. Firstly, we need to evaluate real-world performance. We need to collect a large-scale real user data set. Also, we need to evaluate the user experience that includes a processing delay that is inevitable in the real system. Secondly, we want to mention that the current Dejavu is running on a high-end desktop GPU. However, for mobile devices, you may want to run it on a laptop or even a mobile phone. In order to achieve that goal, you may have to exploit the interframe similarity based on the motion estimation, or you want to reuse part of the neural network. Secondly, I find that knowledge distillation or model compression and quantization to speed up the inference would be a great to do for this work. It is also very helpful to fit the current neural network model into the small GPU RAM that is available on mobile devices. To conclude, I presented Dejavu, a system that leverages similarity across video conferencing sessions to improve future video performance. Thinking about that, it's like you can cache live video content, which could not done before. Second, I want to emphasize that the similar mechanism could be used to apply to a wide range of applications. It could be like a Twitch, YouTube, etc. It could be used to improve the video quality, or it could be used to reduce the CDN cost. With that, I would like to conclude my talk, and I'm open to questions.